What role do simulation environments play in the field of robotics, and how do they contribute to the development and testing of robotic systems and algorithms? Here is the plan for today's tutorial. After a short introduction, we will talk about simulators. How do they work? What happens when you start a reinforcement learning algorithm? Then we will discuss how to model an articulated robot, and we will continue with a small digression on softness and soft interaction. Finally, we will briefly discuss what the students can learn from the data they acquire in those simulations. But before, can we recap what we have learned so far?
We simplified the human hand into parts: joints, bones, tendons, and skin. We also analyzed each of those elements and talked about different fabrication solutions that we could use for them. So you have to remember, for example, there's the flexure joint, the synovial joint, and the rolling contact joint. For now, we only talked about human hands, but we don't want to limit your imagination. For the final challenge, you are free to choose any functional design you can think of, as long as it stays within the given constraints and limitations in the numbers of fingers. Therefore, in the following tutorials, always keep in mind that there might be a better solution than the human hand for your robot. Every time we discuss a task, try to imagine the best design for that task and note it down. Afterwards, you can discuss it with your team and build a robot that implements all of your ideas.
But what if the students have many designs in mind and they don't know how their designs will behave in the design manipulation tasks? Students are thinking about different challenges to test their robot, but they don't have enough time to build many prototypes. They may also have to train their robot with reinforcement learning so that the computer finds the best way to do these tasks. What can the students do to simulate their designs?
So let's start with part 1 of this tutorial, which is on the topic of simulators. We can build a simulation. A simulation environment is basically a virtual platform that allows engineers to model, test, and evaluate robotic systems and algorithms in a controlled and interactive computer-generated setting. This environment emulates real-world scenarios and conditions, providing a realistic digital representation of the physical world where robots operate in. So there's actually many different simulation frameworks that are currently used in robotics. There's SOFA, MuJoCo, NVIDIA's Isaac Gym, NVIDIA's Isaac Orbit, there's Gazebo, there's also Drake, and there's even MATLAB that you can use to build quite easily a solution for your simulation problem.
What are their advantages and disadvantages?
The SOFA is used for a reasonable real-time simulation of soft robots and soft materials. It's especially used for medical purposes, and for this reason, it is extremely useful to simulate completely soft robots. That can be, for example, a soft gripper, or it can also be an anisotropic material. However, this environment so far has some limitations. There's also Isaac Gym and Isaac Orbit, and these are frameworks that were developed by NVIDIA with the collaboration of ETH Zurich. And all of these are powered by GPU-based physics simulation engines. For robot simulation and machine learning, NVIDIA developed Isaac Gym. And as the name suggests, Isaac Gym is a simulation environment specifically created to exploit reinforcement learning. It uses a GPU-based physics engine, and it's trying to physically accurately simulate the environments and also allow the training of thousands of environments at once, all in a GPU-based framework. So I think the innovative power of that tool is to be able to generate functional policies within just a few hours of training. And then you can not only do that for known environments, but also for unknown scenarios and unknown setups. We will talk more about reinforcement learning during a later part of this lecture series. So Isaac Orbit is the latest simulation framework that NVIDIA offers. It has been collaborated with ETH Zurich to create this environment. Isaac Orbit does as well exploit NVIDIA's Omniverse simulation functionality, but it provides a much richer set of machine learning tools. Specifically, Orbit implements now a simplified interface for such features such as reinforcement learning, behavior cloning, teleoperation, motion planning, and so forth. In contrast to Isaac Gym, Orbit is still really pretty much in development, an ongoing project, and they constantly update it to keep it with the state of the art in research. When you compare Isaac Gym and Isaac Orbit, the one thing that stands out is that Isaac Orbit provides you an enhanced frame rate to still do quite photorealistic physics-informed simulations of both rigid robots and also textiles. MuJoCo is a physics engine and a full-featured simulator commonly used for robotics. It's designed for the purpose of model-based optimization with an interest for collision and context. In contrast with a GPU-accelerated simulator, like Isaac Gym, MuJoCo is just CPU-based.
To recap, SOFA is a standalone framework that provides soft body simulation. Isaac Gym is a simulation framework that uses the functionalities of Omniverse. In addition to that, it allows reinforcement learning training and can do soft body simulation, even though it is not optimized for that. Isaac Orbit is an even newer simulation environment. It is powered by Omniverse 2 and allows the application of a bigger machine learning zoo. MuJoCo is a physics engine used in robotics for a variety of purposes, from normal testing of control algorithms to reinforcement learning. It provides its own XML format used for robotic modeling. Which of them can be relevant for our course?
Well, so for the final challenge and also during your workshops, you will create a simulated model of your robot with the MuJoCo XML format. And you will use Isaac Gym to train a reinforcement learning policy for your robot.
Now that we know who is who, how does a learning environment interact with a simulator?
So standard reinforcement learning frameworks are made of two components: the agent and the environment. The agent is the element that decides what to do. The environment simulates the consequences of that environment. At each time step within this loop, you have the following setup. First, the simulator observes the robot and the objects that are occurring in the scene of the robot. And then it extracts from the scene the required state information such as position, velocities, forces, etc. Then the actor computes the next best action depending on the expected reward it will gain. In the third step, the agent passes the chosen action to the environment. The environment then will compute the next states of each object according to collisions and other forces at play. So this cycle allows a never-ending rollout of events. The interactions between all the objects in the scene are computed, and then in the end we have a resulting scene that behaves like the real-world experiment, or even at least close to the real-world experiment. Once you have looked at what a reinforcement learning environment in a single setup does, let's talk about how we can accelerate reinforcement learning. There's not only one agent and one environment, but there are actually n number of these couples of environments, where n stands for the configuration value that is chosen by you. Each environment is independent of the other environments, but for clarity when you train, you see them all together. By simulating thousands of environments in parallel, the reinforcement learning algorithm is actually able to collect experiences faster, and then the training process can be accelerated. Additionally, you can choose the simulation data to understand what went wrong and what went right. Maybe the normal force to the surface of the object was not enough to pick it up. The simulation then provides you with tensors containing information about positions, velocities, accelerations, and forces. So more to that, the weights and biases tool creates graphs tracking loss, rewards, entropy, iterations, and more info that affect the reinforcement learning progress in both training and testing. By accessing these correct tensors, you can directly retrieve information about your robot and apply this information so that you can change your model in an appropriate way. You can define some constraints to understand if an experiment is successful. Weights and biases allows you to see changes in the rewards when you modify your experiment. If you change the learning rate, you can choose different algorithms or try a new configuration of the robot. Maybe you can even add a higher friction layer of rubber to have a better grip on the ball that you're trying to manipulate. Weights and biases will allow you to dive deep into the advantages and disadvantages of each choice you made.
This is very cool, but how can we put a robot in a simulator? How can the computer know how our personalized prototype is structured?
Well, you can just choose a standardized notation for robotics. It's called the Unified Robot Description Format, or just simply short URDF. And there's another format that's called the MuJoCo format, or short MJCF. Both are so-called XML-based file formats that are used to describe sensors, links, joints, the inertia, any collisions, and visual geometries of the robotic systems and whatnot. The URDF is a more popular choice since it is used in the open source robotics framework ROS. But the MJCF format provides you more functionalities, and that's why you will use that format instead. You will be able to put your robotic hand model into text by specifying the distance between joints, how they contact and connect, and which angle they have in regards to each other. The simulator will then take this model and know what the system looks like. It will also be able to solve equations to predict how it behaves in contact with other elements. In the later part of this tutorial, you will see how to write a personalized MJCF file for your robot. So to model softness, you will not explicitly include softness in your simulations, as you will only have a soft skin to cover your hard-fingered robotic hand. But if you ever were to build a fully soft robot, you would have to start by modeling its softness. So for this, watch the next parts of this tutorial to have a grasp of how to do that.
We just went over the main steps the student will see when simulating with their robotic hands. Now we know what happens when we press that start button on our simulator. What have we learned so far? Until now, we have seen some designs that engineers created when building robotic hands. We also understood how tendons and joints are the key players of robotic hands. Tendons transmit the motion of the actuators to the fingers, and joints allow their movement.
But after all, we are in an engineering class. So what we want to know at the end of the day is how to model these fingers in such a way that the mathematical and physical equations come to our hand. So let's go from more general to more particular. Since a human hand is made of 5 fingers, we can assume that each finger is modeled similar to each other. There's just one exception, which is the thumb, and that has one more joint compared to the other fingers. So each human finger is made of 3 rigid links, here, here, and here. And we call these the phalanges, these links. Then there's also tendons and muscles, and finally simply the joints in each finger. Now what we have left are the 3 joints and the 3 links per human finger. This means that if you want to create a one-to-one copy of the human hand, you will need 16 joints. In the workshop, you will be able to use up to 11 actuators for your original design. Again, you can create any functional design of your choice within the constraints. You are not limited to a perfect copy of a human hand. And remember that having 11 actuators does not mean that you can only create a gripper with 11 joints. Once you have your model visualized in your mind, you can start to create the MJCF file that we talked about earlier. This MJCF file is a file with a standardized XML structure. The joints, the links, the sensors, the colors, and the 3D meshes have to be defined each one by one, and for each of those we should add information about their resting position, about their orientation, and also about their dimensions. On top of that, joints connect with links via a hierarchical structure. This means for each joint you will have to specify to which links that joint is connected to. Let's look at this more closely.
Hey, let's get started with MuJoCo. As Robert said before, it is a great tool for CPU-based modeling, so great actually that DeepMind bought and open sourced them to help the robotics community. In this quick tutorial, I'll show you how to get started with MuJoCo through some quick examples that you can try out yourself. Before we get started, you need to install MuJoCo to follow along. Find instructions at the official MuJoCo repository by following this link. Having installed MuJoCo, we can get started by trying out some models that already exist. To get some models, we can head over to Google DeepMind's MuJoCo Menagerie repository. This repo contains a wide range of well-known robots, such as the Franca Amica collaborative robot arm, 2 different robots from Robotics, and a Shadow robotic hand from Shadow Robotics. If you open up a folder in the repo, like Anybody's Animal C, for example, you'll see a bunch of different files. The ones that interest us come with the .xml extension. These are the MJCF files that describe robots and their environment. To view them, we need to run the simulator. Its binary executable can be found in the /bin subfolder of the MuJoCo repo. Bear in mind that I'm on Linux, so the command to run it might be different for Mac and Windows users. Once we run the executable, an empty simulator window should pop up, asking us to drag and drop an XML file into it. Let's try Animal C first. Oops, looks like Animal is falling into infinity. This is because the physics simulation is already running, and we have nothing under Animal to catch it. While we could pause the sim and disable gravity, the wisest solution is to use the available scene.xml file that has Animal standing on an infinite plane. Great, now we have a robot and can play around with it a bit. We can, for example, steer its joints by assigning control commands on the panel on the right. Now, as you can see, it's quite a hassle actually to move joints while the sim is running. Luckily, we can also open files with simulation pause. All you have to do is reload your file, press space, and then you can assign joint values directly while the simulation is stopped. We can open up further models too, like this Shadow robotic hand. After playing around with its joints, I encourage you to have a look at other settings on the left, such as rendering options. The wireframe mode, for example, can make it easier to understand complex joint designs, like this wrist joint here. Now that we've seen some graphical examples, let us start by looking at the XML or MJCF files themselves. Feel free to use any text editor that you fancy, but it's helpful to have something that has XML support so we can navigate the model tree easily. I'm using Visual Studio Code with the XML Tools extension installed. Let's open up a simple robot like panda_nohand.xml to see how MuJoCo files operate. While you're at it, you can also open up the simulator on the side to see the robot the file describes. Then, we can open the XML itself in Visual Studio Code. It can seem a bit intimidating, so I'll collapse all the text first to get clutter out of our way. Now it looks much better. You can see that the MuJoCo file is built up from different tags. If its syntax seems new to you, I advise you to revise the XML standard on this link. Here, we see the MuJoCo element encompassing the compiler, option, default, asset, world body, actuator, and keyframe tags. Now, let's get into the details. The compiler element just tells the simulator some instructions on how to read our robot model. Here, it tells the simulator to understand all angles irradiance, look for the 3D meshes that make up the robot in the mesh_dir subfolder, and assign limits to joints automatically at the end of their respective ranges of motion. The option element adds a parameter to the solver of the rigid body simulation. This is not that important to us currently. The asset element tells the simulator where to find the 3D models of the robot's parts. Note that MuJoCo allows for different visual and collision meshes. This helps in keeping the simulation cost of robots low, as we can define simple meshes for collision, like spheres or ellipsoids, and still maintain nice graphics. After the asset definition comes the most interesting element, the world body. This defines the kinematic chain of 8 links joined by 7 joints that make up the robot. Let's start step by step. Our first link is the fixed base of the robot, called link 0. But we also see a light element that just allows us to see the robot while it's simulating. We see a bunch of geom elements right away. These are the 3D models that make up the base of the robot. As you can see, apart from only one, they are all visual meshes. So they only are there to make our robot appear nice in the simulation, but are not used in the rigid body simulation itself. You can try removing them, reloading the sim, and see if it has any effect on the robot. We also see an inertia element at the beginning of our body. This defines the mass and the moment of inertia. This is not only needed for the rigid body simulation, but it also allows us to do things like dynamically plotting the center of the mass to see if our robot would topple over without support. We see that before the end of the link 0 body element, there is a new body nested into it, called link 1. This is the next link of the robot, which already has a rotating joint connecting it to link 0. We see that the definition of the joint is rather brief. This is as the default element up here already defines how a joint should be parameterized. From here on until the end effector, the pattern is rather simple. Each link contains the definition of its inertia, the joint linking it to the previous one, a visual and a collision geom element, and the next link nested into it. This is how the kinematic chain that makes up the robot is built up. Note that one link may have more than one other bodies or links nested into it. If you're looking for an example, feel free to look at the shadow hand file. After the world body comes the definition of the actuators. You can see the 7 different rotational actuators that make up our robot here. Each actuator has its corresponding joint defined along with parameters such as the gain of its underlying P controller and the control and force range. To see the effect of these, you can, for example, bump up the gain a bit on the first joint and see how it starts oscillating suddenly. Some actuators have less parameters than others. The missing ones were, as before, defined in the default element. The last element is the keyframe. This just defines the starting state of the robot and is fully optional. Our quick glance over the Franca Amica arm and the MuJoCo simulator is at its end. If you'd like to know more about MuJoCo, here are some great sources to get you started. Good luck!
We just learned how to add an art robotics structure to our simulation. We talk about a standardized XML format that is used to build kinematical structures. But how is softness emulated in state-of-the-art simulators? How can we model the softness of human skin? How can we model the softness of silicon, sponge, or even bones?
Alright, so let's start with what we know about elasticity. The first element is a spring. Hooke's law expresses the force generated from a spring when you compress it or you extend it. So now a similar approximation, but a more general, is the so-called Young's modulus. The Young's modulus E is defined with epsilon, which is the axial strain, and sigma, which is the tensile stress. E measures the stress felt by an object when compressed by an amount epsilon. Similar to springs, the bigger the E, the more steep the line will be for this relationship between axial strain and stress. And also therefore you will need more force if you want to even achieve the smallest possible strain. On the other hand, a smaller E, a smaller Young's modulus, characterizes a softer body. And therefore the body is way more extensible. To give you some examples, a sponge can be considered to have a small Young's modulus, while bones will have a very large value for the Young's modulus. This model can express simple soft materials, how they can stretch, how they even plastically deform and break. Materials that present stronger elasticity follow different curves. There are other ways to model softness, but we will not cover them. Here are some names if you are intrigued, such as Poisson ratio, shore hardness, and so forth. If you don't remember, when we introduced simulators, we talked about SOFA, We said that it could easily model softness in real time.
What's the trick?
SOFA uses three-dimensional meshes. Those are just a discretized version of a 3D model. They're made of points, lines, and triangles.
So, meshes are simplified structure. What's their use?
In the physics classes that you had during your bachelor's, you had probably seen the effects of a mass falling on a spring, and then you had to solve some equations using Hooke's law, gravitational force, conservation of energy, and so forth. Now think about what happens when you have a soft interaction between objects. You should solve the equations of the collision for an infinite amount of contact points. For example, when an apple falls onto silicone rubber. Instead, SOFA has to solve equations only for the points, lines, and triangles of the meshes. And that technique reduces significantly the computational time. This can now scale quickly, increasing the complexity of the model. That means nonlinearities, hyperelasticity, and the differentiation reduce the real-time property but deliver results that are a bit closer to reality. This is just the tip of the iceberg. If you're interested in the topic, stay tuned for the next semester's soft robotics class.
Let's say that you created your simulation. Now what?
Now imagine the scenario. Your goal is to pick an object from a flat surface. And you have placed your brand new designed model of a robotic hand into your simulation. You want to pick this object and bring it to a different target location. You start the simulation, the arm, which is not shown here, and the hands accordingly steadily moves towards the object, closes his hand, goes around it, and then quite sadly tries to lift it, but it drops and slips out of the hand. You have failed, but you have also now the ability to learn from that data. I mean, you will not necessarily only simulate one type of task, such as picking up an object. You might also want to hold on to a tool, like you can see here, but you might want to really have that tool keep hammering onto a rigid object, but it can happen that it just slips out of your hand because your grasp wasn't strong enough. And that's just another scenario where you can learn from your simulation data that you have gathered.
But what we talk about today relies entirely on the model of the robot that we gave to the simulator, with friction coefficient, weight, length, density, and so on and so forth. What if we have them mistaken? And is there a way to exploit some real-world experiments? Finally, how do we control our system?
Well, we will have to seek answers to all of those questions in the following tutorials. So to summarize, today we talked about simulation and why do we use a simulator? What is a simulator? And what simulators can we choose from? Then we talked about modeling a hand, and we specifically talked about the MuJoCo file formats. We also covered the question of how can we simulate softness using the SOFA FEM environment. Here we mentioned what a Young's modulus is, what is it used for. We talked about FEM and meshes. And then we also touched onto the question of what can we do with the data from the simulation? What can we access to and what can we make use of using this data?